Hello everyone, welcome back to Explore Electronics. In this video, let's understand Module 1 completely of the subject Fundamentals of Electronics and Communication Engineering with the code 1BECE105 part 205. So here we are going through diodes and their application. This is the first module syllabus. Here we start with introduction, characteristics and parameters of diode, diode approximation, DC load line, and half wave rectifier, full wave rectifier, capacitor filter, only qualitative approach here, and Zener diode and its usage in voltage regulation, then diode logic circuit. These are the content we have. Let's get in and understand each and every concept of this module.
Basically, PN junction diode will be consisting of P-type silicon and N-type silicon. We are going to connect together. So we will be having a P region and N region connected together like this. Then forms the junction. We call it as junction. Wherever the P and N regions are going to be connected like this, we call it as a junction. So one end of P silicon or P-type region will be called as anode. The other end of N-type silicon will be called as cathode. So these two ends will be act as two electrodes. This is one electrode, this is another electrode. So because of two electrodes, this device is going to possess, we call it as diode. Di means two, here ODE representing the electrodes. The symbolic representation of this diode is like this. It is a triangle with a line. This line indicating a junction and triangle indicating the direction of current flow. This triangle is heading towards the cathode from anode. So the current flow will be from anode to cathode and it is in only one direction. And in practically, if you see diodes, the diodes will look like this. Here one end will be a silver region, the other end will be a black region. Here the black region will be P region and this silver region will be an N region. So this will be an cathode and this will be an anode. And if you look at the current flow, we need to make the diode working by connecting the external supply. So this is the external voltage we are applying. When we are going to apply the positive terminal of the battery to anode and negative terminal of the battery to cathode, then it becomes forward bias connection. Similarly, the negative terminal of the supply is connected to anode and positive terminal of the supply is connected to cathode. This becomes reverse bias condition. In the forward bias condition, the current will flow from anode to cathode and diode conducts. We say diode conducts only in one direction from anode to cathode. So here I have shown this is a diode and this is the direction of current flow. And when we are connecting in the reverse bias condition, negative terminal is connected to anode and positive terminal of the supply is connected to cathode. Diode will not conduct, so there is no current flow from cathode to anode. There is no current. So we say diode will conduct only in one direction. That's why the symbol is indicating with a triangle. This is about the current flow. Coming to the biasing of PN junction diode. Initially, when there is no bias means no external voltage is given to the diode. What happens? There is a PN junction like this. Here in the P-type silicon, as we know, in P-type silicon, the majority of holes are there, free holes are there. In N region, majority of electrons are there. When we are going to connect these two together like this, electrons are negatively charged and holes are positively charged. They recombine. You can see in this diagram, this is the N region where the red dots indicating free electrons. Similarly, in the P region, white marks indicating the free holes. You can see here, electrons are penetrate towards the P region and there is a formation of depletion region here. So this depletion region will be having a voltage. Towards N region, there is a positive voltage. Towards P region, there is a negative voltage. We also call it as a barrier. So once the recombination happens, this barrier will not allow extra electrons to penetrate towards the P region. That's why this will be called as a junction potential or the barrier potential. Positive voltage will be appear towards N region, negative voltage appear towards P region. These ions will not allow the extra electrons to penetrate towards P region. So you can see here also in this diagram, these are positively charged holes in the p region, negatively charged electrons in the n region. They are recombined and forming a depletion region here. This is the direction of electric field, and these are immobile ions once they are recombined and settled over here. And this constitutes a voltage, negative over here and positive over here. This will be called as barrier potential, that is Vj. This Vj is 0.6 to 0.7 in silicon diodes, and it is 0.2 to 0.3 volts in germanium diodes. There are two types of diodes we can have, silicon and germanium. This voltage, barrier potential or junction voltage, will be 0.7 or 0.6 in silicon diodes and 0.2 or 0.3 in germanium diodes. Now if we bias the diode, what happens? It will allow the extra electrons to penetrate towards the p region. Let us see the forward bias condition of this PN junction diode. What happens when the forward bias condition? The voltage applied to the junction will be like this. Positive terminal of the voltage or the supply is connected to the anode. Negative terminal of the supply is connected to the cathode. As we know, this n region will be having majority of electrons which are negatively charged. This p region will be having majority of holes which are positively charged. When we are going to connect this positive terminal to the positively charged holes, these holes are repelled from this positive terminal of the battery. Similarly, the electrons are negatively charged. Once we connect negative terminal of the battery to this will repel. So no electrons will come in this direction. Electrons will penetrate towards the p region. You can see here, these are the electrons going towards the p region. And similarly, we can also say holes will penetrate towards the n region. Usually electrons will penetrate towards the hole region, that is p region, that constitutes electron current. This is the electron movement you can see here in this direction. But the conventional current flow, what we say, if the electrons are flowing in this direction, current flow we are going to consider in this direction. That's why current flow will be in this direction. Current flow will be from negative terminal of the battery to the positive terminal of the battery, from positive terminal of the battery to the p region, and then this will be the direction of current flow. Again it will reach us to the negative terminal of the battery. So the question is, here I said there is a barrier potential or the junction potential, that is Vj, which is minus plus like this. So we need to apply minimum amount of voltage over here so that the extra electrons will be penetrate towards the p region. This extra voltage itself should be greater than this Vj. That's why in silicon diode we say minimum 0.7 volts, and more than that we need to apply as a external voltage to make the diode conducts. Then what happens? The barrier potential over here, or the barrier in between the two junction, becomes thinner and thinner. So barrier reduces as we apply the voltage above 0.7 volts. Barrier reduces and electrons flow will be started. You can see here in the IV characteristics, in y-axis we will be having current IF, which is in milliamps. In x-axis we have VF, that is in volts. We started to apply from 0. Since it reaches some cut-in voltage, that is V gamma, called as the cut-in voltage. Why? Because minimum amount of external voltage we need to apply for diode to start conduct. Why? Because this amount of voltage is required to reduce the barrier present over here in the depletion region or in the junction. That's why this VR or the cut-in voltage is 0.7 volts for silicon and 0.3 volts for germanium. After this 0.7 volts region or the voltage, current will be started to increase as voltage increases. And also you can see here, this is the difference in the voltage from this point to this point, and there is a increase in the current, which is delta IF. So this is what the forward characteristics of the diode connected in forward biased condition, and current will be directly proportional to the voltage what we are going to apply. And what happens when we are going to connect the diode in reverse biased fashion? Reverse bias in the sense, the anode is connected to the negative terminal of the battery or negative terminal of the source, and cathode is connected to positive terminal of the source. Here this N region will be having negatively charged electrons. These electrons attract towards the battery since it is positively charged. Similarly, P region consists of positively charged holes. Holes are attracted towards the negative terminal of the battery. That's why the barrier increases. You can see here, this is the depletion region, or this is the junction potential. Here junction potential is increased, or the barrier increased. Since the barrier is wider, there is no current flowing into the diode. That's why we say the direction of reverse current is this, and it is very less. So very less amount of current flow in the reverse biased PN junction. And we say there is no current flow also. No current flow means it is a very less current. So we are going to represent the reverse current IR in microamps, and we are going to represent the forward current in milliamps. Now if you look at the IV characteristics again, this is IF, this is IR, the reverse current. You can see here representation in minus. So as we increase the reverse voltage VR, there is a very small amount of current flow, and it is constant even if we increase VR further, reverse voltage. And this small amount of current flow will be in microamps, and it will be constant till this point. After this point, if we further increase the reverse voltage, what happens? Diode reaches the reverse breakdown voltage. There might be a chance of breakdown of diode. And here the sharp increase in the current, you can see sharp increase in the current is shown over here. This will be called as knee point. Knee point in the sense whenever there is an exponential increase, we call it as a knee. So from breakdown voltage onwards, if we further increase the reverse voltage, diode current will be increased sharply, and there might be a chance of breakdown in the diode. And this is the complete IV characteristics. This is the reverse characteristics. You can see this is the forward characteristics. You can see here IF will be represented in milliamps and IR is represented in microamps, and this will be called as the cut-in voltage. It is 0.7 for silicon and 0.3 for germanium. And this is VF. You can also see here, this is also called as knee point. This is also called as knee point. When there is abruptly change in the current, we call it as a knee point. And here also at the reverse breakdown voltage, we need to observe VBR, and this is the small reverse current. This reverse current will be because of the minority carriers in the diode. And this is also the IV characteristics. You can see here clearly, this is the knee point, this is forward bias characteristics, and this is the reverse bias characteristics.
So the next topic is diode DC load line. So here you can observe this is the forward characteristics of the diode, and we are writing this line on this forward characteristics by taking the point in the y-axis and point in the x-axis. Here we are going to get the operating point of the diode. So to get this, let us look at this circuit. In this circuit, we will be having a diode, and we connected a current limiting resistor here, and we connected to a battery. Positive terminal of the battery connected to the P terminal of the diode, and negative terminal of the battery connected to the N terminal of the diode. Means diode is forward biased now. So once the voltage is applied in this manner, current flow through this resistor, that current is I, and the voltage drop across the resistor can be taken as I into R. So if we apply the KVL to this loop, we will get VDD is equal to VD plus IR. If you write an expression for VD, then VD is equal to VDD minus IR. Now, here in y-axis we have taken current I. In x-axis we have taken VD, that is the voltage across the diode. So to get this point in the y-axis, we need to assume, let's this VD is equal to 0. When VD is equal to 0 in this expression, we will be getting the current I expression as I is equal to VDD divided by R. Just let us assume this VD is equal to 0. Now take this VDD to the right side. This IR become plus I is equal to VDD by R. This is the point in the y-axis. Now let's assume current is equal to 0. When current is 0, VDD becomes equal to VDD in this expression. This term becomes 0. This is the point we are going to get in the x-axis. When current I is equal to 0, we are drawing this. Now connect these two lines, and here it is meeting on the forward biased characteristics at this point. This point will be called as operating point, means Diode operating point is this. Diode will work efficiently when we are providing this much of voltage across the diode and current will be this much. This we call it as a DC load line of a diode.
Let us look at the definition of rectifier first. Rectifier is a circuit which converts AC signal into pulsating DC. So here I am telling it as pulsating DC. Why? Because if the AC signal is like this, the rectifier is going to convert this into the signal like this, not the continuous, not the DC signal constantly like this. So these pulses are present in the output of the rectifier. That's why we are calling it as pulsating DC. This will be consisting of some component of AC also. That's why it is not purely AC to DC converter. It is a conversion of AC signal to pulsating DC signal. And these rectifiers consisting of diodes, semiconductor diodes. You can see here diode working. This is the first half or the positive half cycle where diode conducts. This is the current flow and this is how we are going to get the output. In the second half you can see there is no conduction in the diode, so there is no output generated. So for the one complete cycle, this is one cycle AC input, we are getting only first half of the signal at the output. Second half of the signal is 0. This is how diode works. This can be used in the design of rectifiers. So let us understand the half wave rectifier first. This half wave rectifier is a very simplest form of rectifiers. This circuit makes use of a single diode. Only one diode we are using here in the design of half wave rectifier. And why this is called as half wave rectifier means, if you see the output, this is the AC signal we are applying and this is the output we are getting. This output you can compare with the AC signal, only half of the one complete cycle will be present in the output. So this half cycle is same as the first half cycle. Second half cycle is discarded, means the output is 0. So the third half cycle is present over here. So half of the output of AC will be presented at the output. That's why it is named as half wave rectifier. Now coming to the circuit. How the circuit is built? A single diode we are using and there will be a load resistor RL. Across this RL we are measuring the output V0. And coming before that we will be having a transformer here. A 240 volts AC signal we are applying as input, which is connected to the primary coil of the transformer and it is coupled to the secondary coil of the transformer. This is the secondary coil. This transformer is stepping down the 240 volt input into 12 volts. How to step down this? By choosing number of turns in the primary coil and the secondary coil wisely, we can step down this 240 volt AC to 12 volts AC. Once the 12 volts AC is available over here, in the positive half cycle, this diode conducts. That's why we are going to get the positive half cycle as it is output across RL. And when the negative half cycle of the input is applied, when this is applied, diode will not conduct. That's why there is no current. So output will be 0 over here. Now let us understand the positive half cycle and negative half cycle of the inputs individually. Now you can see here in these two figures, the first one is when the positive half cycle of the input is applied to the rectifier circuit. Here what happens? Diode D1 becomes forward biased. Why? Because this is the positive half cycle of the input. Here this end is plus, this is minus. Even at the secondary coil, this is plus, this is minus. So diode becomes forward biased like this. This conducts the current in this way. So output will be measured from this end to this end. So this is the output we are going to get. Similarly, when the negative half cycle of the input is applied, what happens? This will be treated as minus, this will be treated as plus. So in the secondary coil also we are going to get the voltage in the same way. So diode PN junction will be like this. This P is getting the negative voltage, this N is getting the positive voltage, means the diode is off, or we say diode is reverse biased. Here diode is completely off. In the first circuit we say diode is on, that's why it conducts. Here diode is off, there is no current flow. That's why there is no output. Output will be 0. So if we see the complete cycle, this blue line indicating the input signal and this red line indicating the output signal. This is the peak of the input signal, this is the peak of the output signal, and the DC component will come over here. So this red line indicating two pulses. This is one pulse and this is other pulse. We need to eliminate this pulse, then only it becomes a complete DC. If you have pulses like this at the output of the rectifier, we are calling it as pulsating DC. So this output will be consisting of AC pulses. Now this is the practical circuit of the half wave rectifier. If you apply the AC signal like this, it will convert that into the half wave pulsating DC signal like this. Now the complete DC means, suppose if you have an AC signal like this, the DC output should be a constant like this. So if you are expecting 5 volts, this 5 volts should be a constant. Now we are getting like this. So we need to eliminate these pulses. For that, what we need to do? We need to go for capacitor filter. Okay, before that you can see here, this is the input signal continuously going AC signal, and correspondingly whenever it is going to peak, here also the half cycle is generating according to that. Now let us see the capacitor filter. This is also called as reservoir circuit or smoothing circuit added with the rectifier. Half wave rectifier with capacitor filter. Here you can see in the circuit, this capacitor is added up here. The rest of the circuit is same as the half wave rectifier circuit which we have seen earlier. Now this capacitor is added up. What happens when the capacitor is added up? When the current is flowing in this direction, when diode is on, this capacitor will charge to the maximum value. And we are measuring the voltage across this as an output. The output will be same as the voltage across RL. So this capacitor will be charged to the maximum value. It means the capacitor output will be 0 initially. When this diode conducts, means the positive half cycle of the input is applied, this capacitor will charge. And when the negative half cycle of the input is applied, what happens? This diode will be off. So capacitor will hold its charge, but by the time getting the next positive half cycle, it will get some time duration over here. So this started to discharge slowly, but it will not come to 0. Again, when the next half cycle of the input comes over here, this is applied, again it will charge to the peak. So this process continues, the output will be smoothened like this. In the full wave rectifier, we have two types. One is center tapped full wave rectifier, another one is bridge rectifier. So here we are discussing the center tapped full wave rectifier. In the center tapped full wave rectifier, as the name itself says, the secondary coil of the transformer is tapped in between at the center, and we are splitting the secondary coil as two parts like this. So the primary coil will be given with an AC signal. This AC signal will be of 240 volts, and here the transformer which is using is going to step down the voltage from 240 volts to the less voltage. Depending on the number of turns, it is converting this into 12 volts like this. This center tapped full wave rectifier will be having two diodes, D1 and D2, connected in this manner. You can observe the secondary coil one end will be connected to D1 and the other end is connected with D2. And the center tap here, what we have, will be the reference we are taking for measuring the output and also for giving the input, we can say, from the secondary coil. So this is the negative terminal for the output measurement. Across RL we are going to measure the output. So here there is no connection, so we need to have a circuit like this. So D1, D2 are going to behave in such a way that D1 will be on, otherwise D2 will be on. So let us look at the working. This circuit will be for the positive half cycle of the input is applied. When positive half cycle of the AC input is applied, what happens? Here in the secondary coil, we are going to get the signal like this. So that's why we are indicating this is positive end, this is negative end. This becomes positive, this becomes negative. So this D1 diode becomes forward biased. Because of forward biasing, we say this is on, this will allow the current to flow in this direction. And this D2 diode will be having a PN regions like this. Negative terminal or the P region connecting to the negative voltage. So this is off or reverse biased, we can say. So because of this is off and this is on, the current is flowing in this direction, flowing through RL in this way and come back to the negative terminal like this. So this region will not conduct any current. So across RL, if we measure, this is the direction of current flow and this is the voltage we are going to get as we see in the input side. What happens when the negative half cycle of the input is applied? This is the negative half cycle of the input we are applying. So this is minus, this is plus. So here also we are going to get minus plus like this. So this is the signal we are getting here. Similarly, this is the signal we are getting. So this diode becomes reverse biased. This is the P end, we are getting negative voltage. This is N end. So here D2 becomes forward biased. Why? Because this we are getting a positive voltage. This conducts. So the direction of current flow will be through D2 and it will reaches this point, and through RL the current will flow back to the negative terminal. This is the current flow and there is no connection here. As I said, this center tap will be connected like this, right? These two are having no connection. Here also this center tap will be like this. That's why here also in the negative half cycle of the input is applied, the current flowing through RL will be in the same direction. If we measure the output across this, again it will be a positive output like this. So if you look at the output of the full wave rectifier, this is like this at the output, even if the negative half cycle of the input is applied as a input. So we say in the full cycle the diodes conduct and full wave rectifier is going to generate the full cycle output, and this full wave rectifier output is better than the half wave rectifier what we have seen in the last video. And this is how it is going to work. In the first half of the input, you can see this diode conducts and it is generating the output. When the negative half cycle of the input is applied, this is what the negative half cycle of the input is applied. D2 is conducting and again the current flowing through the RL in the same way this is going to generate. So you can now clearly observe in the positive half cycle the current is flowing through RL in the same direction. Even in the negative half cycle of the input is applied, the current is flowing through RL in the same direction. So if we measure the output across this, we are going to get the two peaks like this. And if you see the complete waveform, it will be like this. This is the input signal AC. This is the pulsating DC which we have converted. It will be having two positive peaks for the positive and the negative half cycle of the input. And this is with capacitor filter. If we put one capacitor over here parallel to RL, what happens? This capacitor is going to charge to the maximum value of the voltage, and then it will keep its charge until the next positive half cycle, next half cycle of the input is coming. So in the positive half cycle, you can see this is without capacitor, the output will be like this. But once the capacitor is connected, capacitor will be charged to the maximum value, and by the time the next half of the signal, means the negative half cycle of the input comes into picture, it is holding its charge and again it will be charging. Again it will slightly discharge, but compared to the half wave rectifier with capacitor filter, this gives more meaningful output. Here the ripples are less and this will be called as a pulsating DC output of the full wave rectifier. And with the extra filter circuitry, we can eliminate these ripples also, and a smooth output will be a DC output we are going to get as output. This is full wave rectifier with capacitor filter, where the center tapped full wave rectifier is connected. Bridge rectifier is again a full wave rectifier. It is working same as a full wave rectifier, but we can have a bridge kind of arrangement of diodes to get the pulsating DC output. It will be called as a bridge rectifier circuit. It will be consisting of 4 diodes which is connected in a bridge fashion. So the diode arrangement will be like this. If we connect this diode like this, and it will be like opposite pair of diodes conduct when the alternating half cycles are coming into an input. Means this diode and this diode will conduct once, and in the negative half cycle or the second half cycle, this diode and this diode will be conducting. The arrangement will be like that. Now let us see how actually this bridge circuit will work. So again, there will be a transformer at the input. It will be having a primary coil connected to a 240 volt AC, and there is a secondary coil. Secondary coil will be giving the step down voltage, something like 12 volts RMS, and it is connected to the diode arrangement. Here 4 diodes are connected in this fashion. You need to remember how the diodes are connected, and they are named as D1, D2, D3, D4 as opposite diodes conducting at that particular time. So at the two ends of this bridge arrangement, we will be having a load RL, and current will always flow in this direction through the load. So we are going to measure the voltage across this RL. Okay. In the positive half cycle, what happens? When the positive half cycle of the input is given to the rectifier, D1 and D2 conducts. This D1 becomes forward biased and D2 becomes forward biased. The current will flow in this direction. Okay. So you can observe here, this is what the path it is going to take to reach the P point when it is the positive half cycle of the input is given. And what about D3 and D4? They are reverse biased and there is no conduction in D4 and D3. And the negative half cycle of the input, is given, what happens? D4 and D3 becomes forward biased. So the current direction will be like this. The current will flow through D3 and again through RL, it will through D4, it will reaches the other point. This is how the bridge rectifier is going to work, and the direction of current will be same in this direction. Okay, so let us understand the working. Here you can observe when the positive half cycle of the input is given, D1, D2 are connected, means D1 and D2 are forward biased and making the circuit closed switch, acting as a closed switch, and the current direction will be shown here through D1 and then through RL, and then it will flow through D2 and it is completing the circuit. And current flowing through RL is in this direction. The output can be measured across RL and output will be again in this manner. When the negative half cycle of the input is applied, the current flow will be in other direction. D1 and D2 becomes reverse biased and D3 and D4 becomes forward biased. So the current flow will be in this direction through this path through D3. Since D3 is forward biased, it will make the path to current flow through RL. Again it will go through D4 and it will reach the other point. Here also the current flow direction will be in the same manner, in the same direction. That's why again we are going to get the same kind of output as we get in the positive half cycle. This is the bridge circuit. Here you can observe the current flow direction when the positive half cycle of the input is given. Here the diode, the name of the diodes like D1, D2, D3, D4 is interchanged, means D3 in place of D3 they have written D4, but the direction of current is the same. So this is what the positive half cycle of the input is given and how actually the current flow will be. And if you look at the negative half cycle of the input, is given. So this will be the path. It makes D4 forward biased. The positive voltage makes the D4 forward biased, and also through this path D3 becomes forward biased. That's why the current is flowing through D4, through RL, through D3 and to the negative terminal. So here we are going to get the output same as the positive half cycle, right? So full wave rectifier output, as we seen in the previous slide, that is a center tapped full wave rectifier. Similarly here we are going to get the output. This is how bridge rectifier is going to work. Here you can observe the output, it is same as the full wave center tapped rectifier. Both center tap as well as the bridge rectifier output will be of same kind. So to connect a capacitor filter or the reservoir circuit to a bridge circuit, it look like this. Again, across the load resistor we are going to connect a capacitor. This capacitor arrangement will reduce the amount of ripples present in this particular output. Without capacitor we will be having more AC component or ripples will be present. After connecting a capacitor, it will remove the ripples present in the output by making the capacitor charged to the maximum value, and it will retain its value, and it is again charging when the next peak comes into the capacitor. That is how we can reduce the amount of ripple getting at the output of the rectifier. What is voltage regulator? Voltage regulator is a device, it regulates the voltage level. Means it step down the input voltage to the desired level and it keeps that voltage as constant during the power supply. Even if power supply varies, the output of the voltage regulator will be a constant DC voltage. So you can observe this is an example for that voltage regulator circuitry. Even if there is a variation in the input voltage coming to the regulator, this voltage regulator will regulate that to 5 volts constant voltage. That can be applied to a mobile phone like a device, we call it as load for a charger. Even if load varies, means the mobile phone changes, it requires 5 volts supply, that 5 volts will be a constant voltage we can get from the voltage regulator. So there are different voltage regulators with respect to the voltage regulation is considered. 5 volt, 9 volt and 12 volt regulators are also available. This is the simple Zener diode based voltage regulator we are going to discuss here. The Zener diode is heart of the circuit here. This Zener diode will be connected in the reverse biased fashion, and RS and RL are the resistances. RS is connected in series, so it is called as series resistance to limit the current to the Zener diode, and this is the load resistance. So let us understand the working of the Zener diode first. The Zener diode, if it is connected in forward biased manner, if it is connected to a positive power supply to anode and negative power supply to cathode, it will be act as a normal PN junction diode. You can observe the forward biased characteristics here. After the cut-in voltage, it varies from 0.3 to 0.7 depending on the silicon or germanium diode, it will start conducting. In the forward biased condition, it will be act as a normal diode. When it is reverse biased, we need to understand carefully. When the Zener diode is connected in reverse biased fashion, you can observe there is a small amount of current, negligible amount of current flow until the point Vz. Once it reaches the Zener voltage, we call it as the Zener voltage Vz, even if current increases to the level of Iz and Iz minimum, the voltage will be constant. Means it will allow the current within the diode up to Iz maximum and at the same voltage Vz. So this functionality can be utilized as a voltage regulator circuit. So Zener diode is connected in a reverse biased fashion is utilized here as a voltage regulator circuit. In this circuit we have RS that is connected to the input of the Zener diode, we can say. So here we are going to get Vz. From these two terminals, if we measure, we are going to get a voltage Vz for a input Vin. So this is a voltage divider kind of circuit here, right? So here we will be having RL across this. So across these two ends, we are going to get a voltage called Vz. It can be written as Vin into RL divided by RL plus RS. So RL is a load resistance and RS is the input resistance. we need to choose this RS carefully. We need to understand what is the maximum level of RS we can give. So the maximum value of RS is RS maximum is equal to RL into Vin divided by Vz minus 1. And the power dissipation across the Zener diode will be Pz is equal to I into V, that is Iz into Vz. The minimum value of RS, what we can have when there is an off-load condition, it is RS minimum is equal to V in Vz minus Vz square divided by Pz maximum. Here Pz is the maximum power dissipation across the diode we can have. So across this RL, if we measure, Vz is the voltage we are going to get as a constant value because of the Zener diode.